and I think they're expanding on this even more. Then we have a little bit of a specialized tool, SysDic. They provide a kernel module, and it can capture system calls. So what they pretty much do is, so you get the same research usage as before, but you're able to actually see what's happening inside the container on a system call level. So you can give, for example, open network requests, which files are open, stuff like that. But we've seen at some of our customers that there is some doubt about installing a kernel module, and sometimes, depending on the system calls you capture, it can have an impact. So it's ideal to quickly research an issue while it's happening, but for a continuous monitoring, it might have a little bit more of an impact than you would like. So, and then to finalize, we have, of course, the APM vendors, New Relic, Ruxit, and AppDynamics. So they're pretty heavyweight. They do deep application monitoring, so you get that code level visibility, which sometimes can be very handy. They were originally designed for monolithic applications, written in specific languages. We've seen that they do have sometimes an issue handling the dynamic nature of Docker, especially in terms of static alerts. And yeah, of course, putting an agent inside the container is a little bit of an anti-pattern. Also, the prices, of course, I think New Relic starts at $75 a month per server, and Ruxit $150, and AppDynamics a little bit more. Now, I want to pick in here on, you have too many dynamic metrics to handle with static alerts. And this is something I really think is important for Docker environments. So they're very diverse, they're very dynamic and very interactive. And it's almost impossible to track all the metrics manually. You don't want to start watching dashboards all day long. Especially, you don't want to set alerts on all these different metrics. So usually what you do is you pick out a couple of ones, but everything else is a little bit in the dark. You don't know what's happening there. So what we think is that anomaly detection is really the way to go there, because it automatically determines if there is a problem. And with most anomaly detection tools, there is not really a need to set it up. There is some configuration you can use, but for example, CoScale works completely automatically, so you don't need to set anything up there. Now, I'm going to quickly show you a little bit of the models that we built at CoScale, so that you have an idea what anomaly detection, what the technology behind does and how it works. So quickly, what is an anomaly? Simply said, it's a deviation from normal behavior. So ideally, you want a system that understands what your normal behavior is and warns you when that behavior changes. Now, up until now, we've, of course, been relying on static alerts, and they are very good at catching these catastrophic events. For example, if your page load time all of a sudden jumps to 50 seconds, there a static alert would work very well. Same with bounce rate or any metric that changes abruptly and very high or very low. But it has its limitation. So
sorry,
there
just a moment, Sam.
Yeah, sorry.
I just need to figure out where the noise is coming from so that I can mute.
Okay, thanks.
Okay. Go ahead.
Okay, thank you. So to continue, so static alerts have their limitations. For example, on a seasonal metric like web request rate, it's very hard to set a threshold there. Ideally, okay, you set it a little bit below or a little bit higher, but then there's the chance you might get an alert every once in a while your system you have more visitors or something like that. Also, static alerts don't really work well with correlation. So there are systems that allow you to do it, but then you have to find the correlations yourself. With anomaly detection, there is a way to automate that, so it gets to know your system, and it might even predict if a change happens in metric A, that metric B will be impacted a little bit later. Or, for example, in this case, you link together the request rate and CPU. I'm going to show a couple of examples a little bit later. And then, of course, as I mentioned before, you have this changing and dynamic environment, especially with containers. So, yeah, your metric might go up or might go down, and it's not as steady as you would expect it to be. Then static alerts will probably give you too many false positives there. Now, there are some challenges with anomaly detection. So one of the reasons that evaluating anomaly detection techniques is not that non-trivial is that even though a situation which is clearly an anomaly, like here, you can see there is a spike in CPU, and then when we zoom on that, we see that the CPU goes from 0 to 4, and mathematically and statistically, that is, of course, an anomaly. It's not really interesting for you as an end user. But then in other cases, it might be. So, for example, a sudden significant difference on a server which belongs to a group of load balance servers for an unknown reason, but the difference disappears and has no impact on your users or your business. Okay, you might say that's not an interesting anomaly, but sometimes, okay, it is, and it can predict something else. It definitely is an anomaly for which you want to be woken up at night, but it might be something you want to research. Now, a simple technique we use is the 3 sigma rule. So we assume all the data that comes in follows a normal distribution, and that data should fall in 3 times the standard deviation from the median. So we then apply this rule to an exponential smoothing technique. So here we have alpha, which is the smoothing factor. And the smoothing factor is basically how many data points from the history we should take into account. And we have a z factor, which is the multiplication factor of the variance. So the 3 sigma rule is in z factor 3. Now, if we look at some data and we apply this rule to it, so here we have some CPU usage. And in blue, you see the signal that's coming in. In orange, you have that median. And then the green is the standard deviation I was talking about. And you see that it's pretty good at finding the anomaly. So all of a sudden, our CPU goes from around 30% to around 50%. And the 2 red dots show us where the anomaly is. And you would say, yeah, this looks pretty good. Now, when we applied this technique to customer data, it seemed to work pretty well. So if you look at this, you think, okay, that's nice. It seems to, this data doesn't look abnormal. We used, in this case, an alpha of 0.1 and a z factor of 3. But if you look closely, you'll notice on the 5th day that we do have abnormal behavior. So normally we have a lot of visitors in the morning, but then not a lot during, more to the evening. But then on the 5th day, we do have a lot more visitors. And this is actually something we want to detect. Now, we did try to tweak the values a little bit. Sorry, one back. So we tried to decrease the bounds, but as you can see, this is of course extreme, but we have a lot of false positives. The other way, we try to then increase the amount of data points we get from the past. So the alpha small is more history, but yeah, then the bounds just became way too big, and we would never detect an anomaly. So our data scientists pretty quickly decided, okay, this is not going to work. We're going to have to find another way. And a technique we see a lot at other companies, and Also, Twitter and Etsy have an anomaly detection library that contains its algorithm, is the Holt Winters, and or another name, seasonal exponential smoothing or triple exponential smoothing. Now, it's very similar to the previous model I showed you, but it takes into account the time of the day. So it takes into account the seasonality that you saw before. Now, after some testing, we saw in laboratory data or generated data, this did what it's supposed to. But then again, when we moved to our customers, we saw, again, too many false positives and missed anomalies. So the technique we ended up using in most of our anomaly detection is a sliding window approach. So we have a model and it keeps taking in new data and throwing out data it doesn't need anymore, and it adapts its model to that. And then this really gives us the adaptivity we're looking for and the stability. So we're getting the anomalies we want. We sometimes still have to tweak with the values and the variables, but the metrics are really good. So simply what it does, we take data from the past. So in this case, we have 6 days. And we're going to try and build a model of what is going to happen in the future. So we're going to try and predict the next 24 hours. And we do this by taking the median. So it's basically the average signal of the past couple of days. We use the median specifically because it's a lot less sensitive to outliers compared to the average. So you see we've extended here to the 7th day. And then we add to that an error bound. So here you see the error bound in red. It's not fixed, which is very important, because we scale it depending on the relative absolute value of the number. So we take into account what the data did before. Here you see the error bound is pretty high during the day, but if we look at the past, we do see that the data sometimes shows us this pattern. So here we have that same spike, and then I think even in the past we have a couple of spikes here. And then the ideal, the reason we chose this technique is because it also really works well at night. When you don't have a lot of visitors, when that error bound becomes really small, as you can see here, we can still detect anomalies. So even if the visitors at night are impacted, you would still get that anomaly, although the change would be a lot smaller than during the day. So then here we see the data that has come in, so the data from the user, and then we compare it to the prediction we made. And then we clearly see that at one point the checkout rate went down and an anomaly was detected. And then this is really, and because we use the sliding window approach, we can take that seasonality into effect. And some of the other anomaly detection systems have problems with this. So and I'll show you a couple of more examples of our anomaly detection further along. Now, what do we do with the anomaly? For each anomaly that comes in, we give it a score between 1 and 100. This score measures how much deviation there was compared to what was expected. So in this example, we had an anomaly. That was pretty high, so we gave it a score of 70%. So we would show this to the user. Depending on the metric, the bound, the threshold is different. We also aggregate anomalies. So if you would have, let's say, 4 or 5 anomalies after each other of only 30% anomaly score, then we still show it to the user because they're very close together. And it might be that some systems impacted each other, and then you would still want to see this. Now, another technique we use, and this is really handy for large systems where you have a lot of servers doing the same thing, so which is called a local outlier factor. This is a technique also used a lot in machine learning. So it works on the principle of local density. So pretty much what we do is we look at all the points and we see how far they are from their neighbors. And the further they are, the larger the chances, of course, that they are anomalies and that there's something wrong. To give you a real world example, so here we have our request rate and CPU user time next to each other. And you can clearly see that you have a group, a nice cluster of points, and then there's one point who is out of there, and that's clearly an anomaly. When used at customers, we also notice that you sometimes have multiple clusters, even small ones, which turn out to not be anomalies, which are just heavy processes or heavy web requests. Now, a problem with this, we tried to use this for our normal anomaly detection on all levels and all metrics, but it has some limits. One of the biggest problems is scaling. Depending on how you scale your metrics, so here, a request is 2 points on the y-axis, and the CPU is just 1, and then of course CPU have to scale it a bit. The distance between the point varies because we are pretty much comparing apples and oranges. We tried it with a lot of different metrics, and we tried some auto-scaling algorithms, but usually they just bring forward way too many anomalies. Now, there's some more information I could tell you. There is a more in-depth explanation of this local outlier factor on the website of CoScale. So if you're interested in finding out more, this was given by one of our data scientists at Velocity. But here I want to stay a little bit outside the heavy details. Now, we used the local outlier factor mostly for load balance detector issues. So when you compare multiple signals, in a load balanced environment, local outlier detection really helps there. And this is also turned out to be really useful for container environments, because you sometimes have then 20 containers and they are load balanced, and then you can compare them to each other and sometimes find issues a lot quicker with one of them than if you would look at the metrics separately, especially in anomaly detection. Now, I think enough about the math for now. I want to show you a couple of examples and just a quick demo of CoScale platform. Now, I want to show you our platform also so you have an idea what's possible for container environments, for the information that you can get, and also, the dashboards that might be useful for you. So quickly, CoScale, we're a company that was founded in Ghent, Belgium, about 4 years ago. We focused on a lightweight approach. So we have a lightweight agent that you install on the server, which brings you server metrics from the operating system. We also now, for the last year, as I mentioned, been working on container and cluster integrations. So we have those metrics coming from Kubernetes and the Docker APIs, but we're also working on Mesos now, and we've recently added Docker Swarm. We have a lot of application integration. So think web services, databases, caching system, queuing system, all stuff like that. We can integrate with a lot of them to get a little bit of an idea, okay, what is the service doing and where is it spending most of its time? And we do this through log files and management interfaces, APIs. And then we have a couple of business integrations, and we have a lot of ways to push custom metrics to our platform, because our goal is really to give you the complete view of your application, going from the highest level all the way down to the bottom, or in this case, going from business all the way to server, or from business all the way to container. Now we add to that contextual events, because a modern environment has many teams working on it. You have an application team, developers, system administrators, sometimes also marketing, which runs campaigns, and this all has an impact on that one environment. So you want to a little bit see what's going on. Excuse me. So we automatically push container lifecycle events. We you can push deployment software releases, infrastructure changes, and a lot of other custom events. Now, a little bit to show you our environment. So we have a very scalable environment. We use a lot of open source tools. So we use Boomerang.js, which is a real user monitoring component. Our agent is written in Go. As mentioned, we use log and API parsing. This all goes to a load balancer and then to our application and real user monitoring APIs, which push it to our main API, which then pushes it to our Postgres, Cassandra, and Elasticsearch, which are main data stores. So Postgres for metadata, Cassandra for all the metrics, and Elasticsearch for all the events. And then we also have RabbitMQ, which acts a little bit as our main component for the anomaly detection, for the alerting, and for the data workers. So all of our other systems react depending on RabbitMQ. Okay, now to quickly give you a demo. So I've set up, I'll try to switch, yeah. Okay, I hope you can still, you should be able to see the application now, but it seems the green border didn't change. Can someone confirm that see the CoScale application? Okay, thank you, Lisa. So so here is the CoScale application as mentioned, and I'm here on our agents page. So this gives you a little bit of an overview of all your hosts and all the machines that are running the CoScale agent. Now, as you can see here by the Kubernetes logo, this is a Kubernetes environment. So we have one Kubernetes master and 10 Kubernetes minions. You can see that the minions all run a Docker plugin. So they gather data from the system. They're completely autonomous, so you don't have to upgrade them manually. You can change the configuration from the web interface. And I want to show off a little bit our in-container monitoring here. So you may have noticed that some of these servers have a number next to it. And the number is the amount of images that are currently being monitored by CoScale. So our Docker plugin allows you to set up the way you want to monitor certain images. So what I do is I say, okay, if you see the image Elasticsearch with a tag wildcards, with all tags, tag doesn't matter, I want you to start the Elasticsearch plugin. And now what our agent does, or specifically what the Docker plugin does, it starts the Elasticsearch plugin inside of the container. And this is really cool for one specific reason is that all the configuration is like you would normally have on a server. Let's say you have a virtual machine running Elasticsearch, you install our agent, you set up an Elasticsearch plugin, and the host name would be localhost and the port would be the standard port, and everything is just accessible. Because our Docker plugin starts the plugin inside the container, it's a little bit the same idea. So localhost is just your container, and the port is just accessible because it's inside that namespace of the container. So you don't have to forward any ports, so it can be monitored. For example, for Nginx, you need to set up a config file, so you don't have to mount that config file to the host system. No, it will just be able to detect it automatically. And yeah, it's also possible to have multiple plugins if you wish. So what happens is our agent and the Docker plugin just watches the machines, is just watching the machine and sees all the containers running and checks the list of configuration it has and to see if it needs to do something. And it automatically adapts. So if containers disappear, it's going to stop those plugins. If new containers come up, it's going to start the right ones. I think I have a question here. So is it the pods I'm referring to? So the servers are the pods. in this case. Okay, now to show you a little bit the information we get from Kubernetes. Here is a Kubernetes dashboard. This is automatically generated, so we create dashboards for all the plugins you install. And you can see here these 10 minions I showed you before. So I can see quickly which containers are running, where they're running. I can also set a couple of thresholds. Specifically here, I have CPU load. So I set a metric on, I selected the metric CPU load and I set a couple of thresholds. And then the containers are going to be color coded depending on how much CPU they use. You can do this for every metric that's coming from Kubernetes. So it's really visual. You can quickly see, okay, how is everything running? I can even quickly filter on them, so to see where each of my controllers or services are running their machines. So that's a really interesting view, we think. And this provides the insight we think you need for an environment like this. Now, we also monitor Kubernetes itself, and we're going to watch for certain events. So in this case, we're going to watch the insufficient replicas. So when containers crash, Kubernetes is going to push up this event, and then you can see it here, and you're able to click through and drill down a little bit. So here is then a Kubernetes details dashboard with Elasticsearch already selected. And I can see the events coming from Kubernetes when we scaled up. We had some containers here that are crashed, as you can see. So a couple of them crashed. We can see that, when they started, when they stopped. So it's really easy to see what your containers are doing. And by the way, if a container misbehaves, this view would become also red. Maybe I see 2 questions. I'm going to come back to them a little bit later.
So just to let you guys know, we are going to have a Q&A session at the end. So if you can hold your questions, then we can cover them at the end.
Okay, that's awesome. Here you see, by the way, the same view as we had before, but then on the replication controllers and services level. So you see we have 3 replication controllers and 3 services, and then you can quickly see the containers that are supporting these services or controllers. By the way, something that I haven't mentioned is because we select a time frame, and sometimes it can happen that containers stop during that time frame. Containers that are currently not running anymore are shown a little bit opaque. To continue, here you see then actual data that's coming from inside the container. So we have a couple of Elasticsearch containers running, and at one point we decided to scale them up to 20 pods. You can see it here going from 10 to 20. And automatically, so without the need to change any dashboards or configuration, these new containers are detected, the right plugins are started, and we're going to gather all the Elasticsearch metrics we can. So the list is very large. I can maybe quickly show it. So here for Elasticsearch, you see that generally we don't really filter on those. So these are all just really coming from Elasticsearch. Then now this is of course very low level. I want to show you this example because this is really a high level dashboard. So here this is a dashboard, for example, you could put on a wall in your office. And this gives you a little bit more of an overview on how your application is doing. So we have a conversion rate, which is coming from Google Analytics in this case. We have a couple of APIs. We have the performance of these APIs on all our different servers. We have our page load time coming from our real user monitoring, the error rates, anomalies, and then free memory CPU load. Now, here again, we have this drill down functionality, so you can link dashboards together. So I click now on our real user monitoring and I arrive on a different dashboard, same time range is selected. And here you see a nice example of our event system. So these little icons under the charts give you the events and give you a little bit of context of what's happening. So here you see a marketing event. Now our anomaly detection did detect something at the same time, and I'm going to show you a little bit later. But you can see how they provide some insight. And you can keep actually going lower and lower. So this was a global view of my website. So now I'm on a specific page view. So I get my page views, page load time, and then see which resources are used in the front end. And again, I can click through and I arrive on a container level. And I get a little bit the information coming from the web service. We also have some database integrations. So this is the heaviest query on a database, a little bit CPU load, memory usage, also the most run queries. Web services, so we get latency for every page, error rates. You can visualize this then on a heat map, for example, to see the changes over time. Because I think here you see this one used to be red, and then there was a fix at one point, we know, and then see that the color still becomes red sometimes, but it is improved. Now, to finish, I talked a lot about anomalies, so to show you a little bit of an example, here we have our anomaly timeline, and we split up our anomalies into 3 levels for a couple of reasons. The most important one is not every anomaly is super important, like an anomaly on a server level, which has no impact on your user or business, is not something you want to be woken up for. Of course, an impact on business is very important. So so here we have an anomaly on conversion rates. We have an anomaly on latency. I'm going to click them open on request rates. And then we also have 2 anomalies coming from a server level. So here is a bar chart that shows you in blue what the data was from the past, so the data are anomaly detection used, and then red is the data that's flagged as an anomaly. So we can see that we indeed now have a lot of users that are experiencing page load time higher than 5 seconds, and a lot less users that are in that 300 milliseconds to 1 second. Then our page views are higher. You can see the anomaly every time pink. On 2 specific pages, our page views are higher. And then we see also that the CPU user time is also a lot higher on 2 servers. Now, in this case, it turned out to be that our marketing team did a large campaign. Our servers were not prepared. CPU time went up, and the latency was impacted. And then with our forensic system, I can quickly see that Nginx was indeed the software that caused the issue. To give you another example of an anomaly, and this is coming from a customer of ours in the US. So they had an existing anomaly system, which they used only on business data. So we didn't adapt our algorithms for their data, and it quickly found a little bit, a couple of anomalies in their old data, which they sometimes didn't find themselves, and sometimes we found it a lot quicker than they did. But here is really a good example. Here you see a metric that has a daily pattern, and all of a sudden there is a drop, which is very hard to detect with static alerts. And you see that our anomaly detection flagged it as, okay, this seems wrong. Maybe you need to check it out. I think that's, to summarize maybe a little bit what I've just shown you, I think is really what you need for container environments. You need to see what's happening inside that container. So, to end, I don't know, I see there are a couple of questions. So,
thank you, first of all. And the way we're going to handle questions, and if you've been to one of these before, you already know, please send the questions to me in a private chat, and I will read them out loud. We do have those questions that we did not get to before, so we can start with those. Sam?
Okay. So yeah, the metrics we grab, for example, Elasticsearch. Yeah, that's, as mentioned, usually everything we can. We don't do any limiting on that. We're not going to choose metrics. Every system is a little bit different, and usually the people who are monitoring it know better than us. Our anomaly detection does pick out a couple of metrics to watch first, because it would be too heavy to run the anomaly detection on everything. So we're going to monitor a couple of key metrics, and then when we see that they misbehave, we're going to expand to all the other metrics. Then, does your product show the relationship between individual microservices? Currently, we do not. This is something we want to add. We actually have a research project for this, which is supported by a couple of parties. So we will be expanding on this in the future. This is really something we want to work to. And then last, so the monitoring works by adding a custom container to user-defined POD. This action container is responsible for monitoring particular service, for example, pulling the service via localhost and then sending the metrics to CoScale servers. Not 100%. So we're going to start, you can install our agent as a container. You don't have to. You can just also install it on the host operating system. But we don't really start a custom container. The way Docker works is it creates a namespace for each container, and then creates a network interface and a couple of other things. And we're going to just start one of our plugins inside that namespace. So it doesn't really add another container to your system. Probably if you send me your email address, I can give you a little bit more technical information on how we do it. And yeah, I hope that answers your question a bit. Okay. Yeah, I think that was the last question. I don't know if there are any others. Seem to lost. Yeah.
Okay. This is better. All right. So if you have any questions, now's the time to do it. There we go.
Okay, that's a good question. We aim for 1% with a maximum of 2% impact, generally on all different metrics. We have a built-in mechanism for the agent itself that it will warn us if it's using more than 2% CPU. So we can research.
Okay. Any more questions coming up, folks? All right. So, there we go. What about BW consumption by the agent?
Bandwidth, or I'm unsure, B/W.
Randy, would you care to elaborate? There we go. Okay.
Yeah, it's a good question. So maybe to answer that, we push as minimal. So we gather on an agent level already minute data. So CoScale works on minute data. So we're going to gather the metrics, of course, a lot quicker on a host level. And then every minute we're going to push through HTTPS to our APIs. Now, to give you a little bit of an idea how low we would like to keep it, is for CPU, we only send the average amount of CPU used. Now, sometimes you want to know, of course, okay, which process is using more CPU, and then with the average, that's not possible. Now, a customer came to us for this, and he says, "Okay, I want to see the CPU of all my programs." And we said, "Yeah, well, no, that's a little bit against our philosophy." And this is one of the reasons that we started with a forensic system. So forensics is a little bit like lightweight anomaly detection on your server. It detects a change, takes a snapshot of what's happening, and then pushes it to our system. Again, keeping that bandwidth down, so we don't send all the logs to our system and stuff like that. So it should be very minimal.
Okay. And how do you support the root cause of anomalies?
Yeah, that's a good question. One we get a lot. So currently, it's very hard to see the root cause of a change in the environment because, as mentioned before, we don't show the relationship now between microservices, or we don't have that information. What we do have is that we bring together all the metrics that changed. So it does become a little bit easier to see the cause of an impact, because you have all these metrics that show abnormal behavior. But we're not at a level yet where we can say, okay, your website was down because of that container. But that's something we would like to do, of course.
Okay. Is there any code level drill down?
No, that's a specific choice of us. So because the lightweight part again, because the code level visibility does add some overhead. And also we feel that usually in a production environment, you're more interested in which web requests are misbehaving. And then you go into a development environment and use those code level drill down tools like New Relic, for example, to see, okay, what's actually happening there and why is it so slow on our production servers. Okay.
Okay. And do you have an open source version?
No, we have some open source code on GitHub, and we may expand that in the future, but currently CoScale is a closed source solution.
And how do you support hybrid environments?
Let's see if I get the question right. You mean a lot of different operating systems, stuff like that, hybrid cloud? That's a good question. So our agents are built in a way, so you build an agent for a specific type of server, for a web server or database, and you can then install that agent on as many machines as you like. For example, if you have an Azure image and you scale it out and it has a CoScale agent installed and you scale it out to 10 active servers, those servers are going to be automatically added to CoScale and it's going to start monitoring what's happening. We also support most configuration management tools to be able to support these environments. I think I'll take the next question. Okay, so security concerns. Is it then in the area of the data being sent to CoScale, or where? Yeah, okay. Because we normally only send numbers, we sometimes send the log line. So the data we have is normally not that valuable, you could say. We, of course, apply most rigorous security standards for our own infrastructure to make sure nobody can access the data from outside. We're also a European hosted company, so our data is in France, which has very high privacy and security laws. But even if that is not enough for you, we have also an on-premise version which uses Docker, by the way. So even then, you can install it on your own server. I don't think, yeah, depending on the number of hosts, an average server would be able to handle our environment. Okay.
All right. You want to go ahead and take that one, Sam?
Yeah. So pricing, we're a host-based pricing model. We come at about 50 euros a month per server. This includes everything. So for every host, you get a certain amount of containers. I think it's 20 containers. And yeah, page views and everything's included. So we don't have different prices. For the on-premise, it's the same pricing, but there is a setup cost, one-time setup cost. And our pricing does scale with the amount of servers you have. So if you have 1,000 servers, the price per server does become a lot lower. Okay.
Okay. So we are running a bit out of time here. So I'm going to end the Q&A session unless anyone has a really pressing question. And Sam's email is right there on the screen. So if something comes up when you're driving home or when you go to watch something on TV tonight, you can just send him an email there. Yeah. Thank you again, Sam. Wonderful presentation. And just remember, everyone, that we do this every other week. We will announce the speaker for next week by the beginning of this coming week. And that's about it. We're going to put up the video of this presentation very soon, in the beginning of next week. And you'll be able to watch it in case you want to remember something. If you have any suggestions or any comments, you can feel free to leave them on meetup.com. And Sam, thank you very much for coming.
Yeah, thank you too. It was a wonderful experience.
Great. All right, folks. Have a good night.
Bye, everyone.